So this lesson is on continuity. We have done continuity before. We're just going to use a little bit more of a grown-up, like calculus definition for it involving limits now. In layman's terms, continuity means you can trace the graph without lifting your pen or pencil off the paper. Do you know what I'm saying? There aren't any holes, breaks, asymptotes, or other emotional problems in the graph, okay? But like I said, we're going to use a little bit more of a grown-up calculus definition for it. So in order for a function to be continuous at a value c, whenever you write a definition, you have to do the like in general one. When we do a problem, it'll be an actual number like 3 or 7 or -2. Do you get what I'm saying? Like, but for right now, it's going to say c. First of all, f of c exists. And what that means is there's a point there. You don't have a void. You don't have a hole or an asymptote or something like that. Like there is an actual point there. Does that make sense? To be continuous, there's got to actually be something. Okay, cool. Second rule, there's 3 of them, by the way. There's 3 rules. Second rule, the limit as x approaches c of the function. So limit as x approaches c, and again, when you do an actual problem, it'll be like limit as x approaches 2 or something, also exists. What that means is that there's behavior on both sides. Both sides come to the same place. Do you get what I'm saying? Okay, so like when you zoom in on it, both sides are meeting up. So there's a point, there's a limit, and the last one is the one that gets everybody because writing it is a little bit longer. But it's there's a point, there's a limit, and they agree. They equal each other. So what I'm going to do is take these 2 statements and slap an equal sign in between them, all right? So the limit as x approaches c of the function equals f of c. So there is a point and there is a limit, and they equal each other. So those are the 3 parts of your definition. So types of discontinuities, I'm going to show you the ways that those 3 rules could be broken. So let's break the first rule. I know, I'm like, here, let's break rules. Let's break the first rule and say that f of c does not exist, that there isn't a point. There's 2 ways that can happen. Can anyone give me one of them? There's 2 ways you cannot have a point. An asymptote is one, and then somebody said the other one, a hole. So if you have an asymptote, that's going to break that rule. Or if you have a hole, that's going to break that rule. Now, I'm just going to do this verbally because I don't have to write this over and over again. But we did this earlier this year, too. One of those is what we call removable. The other one is non-removable. Which one is the removable one? The hole is removable because it's like you just removed the point, and you could fix it and make it continuous again if you put the point back. This is a more deep-seated issue. You can't just stick a point back in there and have the 2 pieces link up. Do you get what I'm saying? You guys look tired, but you're staying with me, so good job. Okay, that's the ways you can break the first rule. Now we're going to break the second rule. Limit as x approaches c of the function does not exist. There's one way this can happen, where your limit does, well, actually, having the asymptote here, the limit wouldn't exist as well, but there's one other way. How could you have the limit not exist? What would it look like? It's a type of discontinuity we've talked a bunch about. A jump discontinuity, good. So the 2 sides don't go to the same place. So if you were to zoom in, like this side goes up here and this side goes down here. Is that removable or non-removable? Non-removable, good, I can't talk. You can't fix it just by putting a point back in there. And then our last rule is that the limit and the point equal each other. So the way that that rule would be broken, and again, writing this bothers people, but I'm just going to recopy this statement and say not equal instead. Like I literally just rewrote this and slashed through the equal sign. It means that you have a limit and you have a point. So you have all those things, both of those things, but they don't equal each other. This is the haha tricked you. The point's over here. Now, do you remember the one I'm talking about where you take the point, steal it, and put it somewhere else? Okay, it looks like this. So you have an actual point and you have a limit. The 2 sides come to the same place, but they don't equal each other. Bless you. And that would also be removable because you just removed the point. So these 2 are removable. And then the jump and the asymptote are non-removable. Listen. What gets people about this is the notation and how you have to write this, but it's, you got to get used to the more grown-up definition. In essence, the material's not hard. You just kind of look at a graph, but you have to be able to write that stuff. But anyway, here we go. We're going to look at each of these points or intervals and state whether the function is continuous or not. And if it's yes, that's great. You just write yes and you move on. If it's no, you have to like state which rule got broken, and that involves writing a little bit, but you'll be okay. Okay, so let's look at 4. Everybody look at 4 with me. Here's 4. What do you think? Yes or no? Is the function continuous at 4? Correct. No, and you're going to get that by instinct probably. Now you want to go through the rules in order. There's a point, there's a limit, they agree. Because that's in order easiest to most difficult. Start with the easiest. There's a point, there's a limit, they agree. So when you look at 4, is there a point at 4? No. So you're going to say f of 4 does not exist. Now there's also not a limit at 4. So you could also say limit as x approaches 4 of the function does not exist. But this is easier. Go with the easier thing. All right, let's look at -2. What do you think about -2? Yes or no? Continuous or discontinuous at -2? Yeah, discontinuous. That's a no. Now you want to go through the rules in order. There's a point, there's a limit, they agree. At -2, is there a point? Yes. Okay, so the first rule is actually good. Is there a limit, like both sides come to the same place? No, it's a jump. So we're going to say limit as x approaches -2 of the function, and you have to put that f of x there because otherwise it's not of any function, does not exist. Limit as x approaches -2 for the function does not exist. There's a jump. I get people on the quiz that write, there is a jump. I won't take that. You have to use the definition because they won't take that for the AP calculus exam either. And teaching you calculus. All right, let's look at 3. Here's 3. Just watch me point to it. Here's where 3 is. Is the function continuous here at 3? Yes. You can trace through 3 without lifting your pencil. So yes, which is great because then that's all you have to write is yes, and you get to move on. All right, -6 is right here. What do you think? Yes or no? That is no. Go through the rules in order. Is there a point? Is there a limit? Do they agree? So is there a point at -6? No. Good. So you're going to write f of -6 does not exist. It's the easiest one to write. So go with that one. Like go with the easiest thing. All right. What do you think about 5? Here's 5. That's a no. And what's the reason? What's going on at 5? There isn't a point, so we're going to write f of 5 does not exist. All right, and then look at 1. Here's 1. What do you think? Yes or no? That is no. Now, watch me point to this. For 1, there is a point. And there's also a limit. Both sides come to the same place. So there's a point and there's a limit. What's the problem? They don't equal each other. Okay, so we're going to write limit as x approaches 1 for the function. Limit as x goes to 1 for the function does not equal, it's like a no parking sign, f of 1. So there is a point and there is a limit. They just don't equal each other. Now, the rest of these are intervals. So it's like from here to here, and it's a span of numbers. If it's a no, you only need to talk about where the problem happened, not the entire span of numbers, okay? This is from 8 to infinity. I'll try and cover up everything else. Just watch me point to it. Here's 8, and then onwards forever. Do I have to lift my pencil off the paper to trace that? No, okay, so it is continuous. We're good. From 8 until forever, there aren't any problems, which is nice. Now, from -5 to -2, I realize that looks like a coordinate point. It's from -5 to -2, but the parentheses mean what? Do we want those points or do we not want those points? We don't. Okay, so we don't need to include the -5 and the -2. Okay, so let me try and cover up everything -5 to -2. There we are. So do you see -5 to -2 there? What do you think? Are we continuous in between -5 and -2? Yes. It doesn't matter that there's a hole there because of the parentheses. We're not including it. So that is continuous. Follow-up question, if there were brackets, then it would be discontinuous because at the -2, you'd have a hole. Okay, but we kind of lucked out there. We can just say yes. All right, from 5 to 7, and you have to include the 5 and the 7. So let's see. Here's 5 to 7. I'll cover everything else up. What do you think? That one's no. And what's the problem? F of 5, there's a hole. F of 5 does not exist. And then the last one is from -1 to 1 with brackets. So you're including the -1 and the +1. So again, here, I'll try to cover everything else up. Here's -1 to 1. What do you think? Yes or no? It's no. And the problem is at 1. What's the problem at 1? They don't equal, okay? So it's limit, and don't flip this over as soon as I'm done writing this because there is actually one extra thing we're going to add. Limit as x goes to 1 of the function doesn't equal f of 1. There's one other thing I'm going to have to add into that because we're only looking from -1 to 1. We have to approach 1 from which side? I'm approaching 1 from the left. So you have to put that little negative in there to show you're approaching it from the left. Again, these aren't like hard to understand. It's just hard to write because the notation, like the yes or no, you're going to get from looking at it. Like instinct is going to kick in and you're going to be like, hey, that's not continuous. Do you understand what I'm saying? It's just the notation that you have to get used to. Now go ahead and flip it over. These we've actually done already this year. So this is going to be review. Find P so that the function is continuous. Look at, if you want the function to be continuous, you want the two pieces to do what? Connect. So you're going to set them equal. All right, so you're going to take the first thing, x squared minus 2, make it equal x minus p. If you want it to be continuous, set them equal. Is this ringing any bells? We did this way back when. We did this with the piecewise functions, which would have been like November. I realize that was a long time ago. All right, and then you're going to plug in for x. What number do you think? Plug in -1 for x. So you set them equal, you plug in whatever the number is, and then we're going to solve for p. All right, so let's see what this gives us. -1 squared. The +1 minus 2 is -1. And so weirdly, what happens here when you add over the 1, yeah, you get 0 equals -p. Well, you can't, I mean, 0 divided by -1 is still going to be 0. You can't positive or negative a 0. So we actually just ended up with 0. Actually, that problem feels so familiar to me. I think I may have copy and pasted that from our notes back because it's not different material. All right, let's try it again. Set these two things equal. You have p squared minus 2p plus x equals x squared plus 3. Oh, and don't stop listening to me when I finish this because I'm going to show you your delta math real quick and do a problem or two with you so you can understand how that works. And then what number do we plug in for x? 4. Good. So plug in 4 for x. So everywhere there's an x, put a 4. This isn't calculus, really. This is more algebra. Like this is like algebra 2, basically. All right, so this side's not going to change. This side, 4 squared, 16 plus 3 is 19. And then how do we handle that? Make it equal, evacuate. Do you remember me saying evacuate, evacuate, make it all equal 0. We're going to subtract over the 19. Well, 4 minus 19, be -15. And then what? Factor it, okay? Like our warm-up that we just did here. So we're actually going to get 2 answers. How would you split up 15? 5 and 3. And then what symbols to get a -2? Yep, -5 plus 3. And so when you set those equal to 0, you get P equals 5 and P equals -3. Actually, I wrote really big for them. Bless you. All right, hold on 1 second because I'm going to show you how the delta math works. But hold on, I need to get there before I share the screen. Okay, are you all watching? Okay, because I don't want to answer 4 billion questions later. I don't mind answering questions, but I want to like avoid them if possible. So there's 3 sections. Let me do the last one first. This is what we just got done doing. You would set these equal and then plug in 18. Do you see what I'm saying? You would have to write that down though. Like you can't do that in your head. You would have to actually write something down. All right, for these ones, this is super easy. Is the function continuous at -3? Here's what you would do. You would plug in -3 to the first piece. You would plug in -3 to the second piece. And how would you know if it's continuous? If they equal each other. Very good. We have common sense. Okay. And then the other one, we'll do a couple of these together. It's drop down menus. So all your choices are here. We're looking at -5. So when you look at -5, is the function continuous at -5? Yes. Okay. Now we're going to do the drop down things. Limit as we go to the left for -5 is -7. Limit from the right for -5 is also -7. And so the limit exists and is equal to -7. Do you see how I did that there? I'll do another one that hopefully they're not equal and I can show you what happens. Furthermore, it can be seen that the actual point there is at -7. Therefore, the function is continuous because limit, oh, there we go. The limit as x approaches -5 is equal to the point at -5. Okay, hopefully the next one won't be, and I can do an example that's not. Where's this? Oh, 4, see, that's continuous. I want to do one that's like not. Hold on. Where's this one? 3. Oh, 3. Are we continuous at 3? No. Okay, let me show you what goes on for 3. What is your limit for the left for 3? 5. What's your limit to the right? 5. So the overall limit exists and is equal to 5. But the actual point does not exist. Okay, DNE. Therefore, the function is not continuous because what one is this? The limit as x approaches 3 exists, but doesn't equal f of 3. Do you see how it works with all the little drop downs? Okay, I just don't want you to have a zillion questions later.